Let me walk you through the code. So the first thing that I would like you to notice here is this line when I am loading the input dataset to train the model. This is the dataset that we have discussed in the previous slide, which contains predictors and target variables. We need to do some transformations on this dataset. First, you can see here we drop some variables that we don't need. Then we normalize the column. This is a common best practice in machine learning. And of course, we also need to split the dataset into parts, one for train and the second one for test. What follows here in the code is some reshaping that is required to put the dataset in the correct input form to be ingested by a neural network. As a matter of fact, for this example, I have chosen to build a simple neural network. Don't take it as a recommendation. There are many algorithms that one can choose for the energy demand forecasting, which is a sample of time series forecasting. So possible approaches for time series forecasting spans from classical models such as ARIMA or random forest to more complex deep learning models, including, for instance, recurrent neural network. Here I wanted to build a simple exemplar, so it's not definitely something that is ready to be taken into production, but it is good enough for demonstration purposes. What I wanted to notice here is the shape of the layers of my neural network. The first layer has a number of neurons that corresponds to the numbers of predictors in our dataset, while the output layer has 24 neurons. This means that the output of our algorithm will be an array of 24 numbers, each one representing the expected energy demand after 1 hour, 2 hours, 3 hours, up to 24 hours, starting from the model where we produce the forecast. The last part of the code, in particular this fit function, launches the training of the model, and this one is basically saving the trained model so that it can be used later on for inferencing. Let me now run this code locally by typing python train.py, and here you can simply see that the model is starting to run. And when it has done, you see that we have this neural network file, which is the trained model that was produced by this piece of code. Now you can see that the training was quite fast, and this is because I am using here a small input dataset for demo purposes. Normally, working with a full dataset, it's better to train on the cloud, and we can do it using SAP AI Core. Now, to run on SAP AI Core, we need to wrap this code into a Docker container. That's why you see that here I have prepared a requirement.txt file that lists all the Python libraries that I've used in my code, and a Docker file with instructions to create this Docker image. So the image should be based on the Python version 3.9. It should install all the requirements, and it should also contain, of course, our training Python script. Now I can create the Docker image using the docker build command at the command line. And I can upload it in my Docker Hub, where AI Core will be able to find it and grab this Docker image. Now, for sake of time, I will not show you in this demo how we can train the model step by step. There are many tutorials where you can learn how to do it, and you will have references at the end of the presentation. Here, I'm just gonna show you that I have already created an execution in SAP AI Core, which, as you can see, completed successfully. And the execution output is a file containing the trained neural network, which has been written by SAP AI Core in our cloud storage, which is in this case an Azure Blob Storage. So here you can see this file that can be used for inferencing on new data. So that was it for the training of our model. Let's see how the inference works instead. So here is a Python script that I have written to mimic what we want to happen daily in the smart home devices of our prosumers. So for a given prosumer, say John, on a given day, we will have certain weather conditions and certain electrical load data. And of course, we will have also a specific history of how weather conditions evolved in the last days, weeks, close to John's place, as well as a history of how electricity was used by John in the previous days or hour or weeks. For instance, how often he has been doing laundry, if he has been heating up his house or not, etc. And based on that, we want to forecast how much electricity John is likely to consume in the next 24 hours. First of all, we need to load the trained model, which I have downloaded here locally. Then we need to prepare the predictors. So here in my code, I am extracting randomly the electrical load predictors and the weather predictors. Now, in reality, the electrical load predictors come from the smart meter. So the smart home device will have this information. No need to extract it randomly, of course, in reality. And on the other side, the weather predictors will be communicated to the smart home device by BTP. We will see extensively how it works later on. But for the moment, imagine we have the correct predictors here related to John's house for today. Here I am putting them together, then I am normalizing them. If you remember, this is a common best practice. We have done it also in the training phase. And here I am submitting these predictors to the trained model to obtain my forecast. So y hat is the array of 24 values giving me the expected energy consumption for John in the next 24 hours. This value from the smart device will need to be communicated to BTP, and we will see how it works later on. For now, I'm just printing out the result. So let me just run the code. And you see here that according to the model, John will consume, for instance, this amount of kilowatt hours in the next hour and this amount of kilowatt hours in 24 hours from now. So this piece of code that I have shown you can be wrapped into a Docker image and deployed wherever we want this code to run. In this case, we want to deploy the code at John's place in his smart home device. So to do that, we need to rely on an external IoT platform, and Jacob will show you how this works in the next session.